In this lecture, we will continue our discussion on theorems on open sphere and open set. In a metric space, arbitrary union is open and finite intersection of open set is open. In a metric space, arbitrary union of open set, okay, open set is open and finite intersection of open set is open. In the statement of the theorem, it was asked to prove that arbitrary union of open set is open and finite intersection of open set is open. Proof. Let X be a metric space and Gi be arbitrary class of open set. Arbitrary class of open set in X. To show arbitrary union of Gi equal to C is open. There arises two cases, either G is empty or G is not empty. If G is empty, then G is automatically open. We have nothing to prove. If G is empty, then we have nothing to prove. G is open because empty set is open set. Okay? If G is not empty, then we have to prove this theorem that arbitrary union of open set is open. If G is not empty, then for all X belongs to G, X belongs to the intersection. X belongs to the union, not intersection. Union of Gi. This implies X belongs to Gi for some I. Okay? For some I. As is Gi being open set, there exists some real r greater than 0 such that SR hex is contained in Gi for some okay. If SRX contained in some Gi, that means SRX is contained in the union of Gi. Therefore G is open. That means arbitrary union of open set is open because I am content for any hex in G, I will get some open sphere that is contained in G. So G is open. Next, we are going to show that finite intersection of open set is open. Secondly, let Gi I ranges from 1 to n be finite class of open set. To show finite intersection intersection G is open. G is open. If G is empty, then G is open. G is open. If G is not empty, if G is not empty, then for all x belongs to G, x belongs to the intersection, finite intersection Gi, I ranges from 1 to n. That means this implies x belongs to Gi for all I ranges from 1, 2, n. Okay? As is Gi being open set centered at x, we will get some open space containing is Gi. So right, there exists some real number Ri greater than 0 such that as Ri x is contained in Gi for all I ranges from 1 to ... n. Okay, let R be the minimum of this R1, R2, Rn. Okay. If G is not empty, then for all x belongs to G, x belongs to the intersection. That means x belongs to is Gi for I ranges from 1 to n. Is Gi being open set, there exists some real number R1 greater than 0 such that Srix is contained in Gi. If we take R equal to minimum of these Ri's, that is R1, R2 up to Rn, then Srx is subset of Gi for all I ranges from 1 to up to n. That means this Srx is a subset of the finite intersection of Gi, I ranges from n 1 to n Gi. Since for each x belongs to G, we will get some open sphere containing G. Therefore, G is open. G is open. We will get this open sphere containing this G. That means G is open set. That is a finite intersection of open set is open. In the second case, finite intersection is necessary. Write a remark. Write a remark. Finite intersection is necessary because consider 1 by m minus 1 by m plus 1 by m arbitrary intersection of this 1 to infinity. Then this will be your singleton 0. That is, first if you take n equal to 1, this will be minus 1 to 1. If we take n equal to 2, this is minus half to half. In this way, it will come nearer to 0. And as if you take arbitrary intersection, it is a singleton set 0. and with 0 as center, if I draw an open sphere as epsilon 0, that will not contain in this set 0. This will not contain in this set 0. Okay, this will not contain in this set 0. Therefore, finite intersection is necessary. This set is not opening the set of real number. Because right properly, because since as epsilon 0, that is open sphere center at 0 and radius epsilon is not contained in single constant. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.